Ok, então boa tarde a todos. Vamos começar. Sorry, in English, right? This one. Okay. So let's get started with part number 11. About geometrical transformations. So you've seen in today's theoretical class exercises 1, 2, 3, and 4, I believe. Yeah, 4. So right now, having understood the basics of transformations, we are going to start using dedicated ROS packages and nodes, functionalities that actually do a lot of what we need to be able to draw a robot, an articulated robot. So the idea is that we start developing our own robot description. Robot description is done in Urdf format, which stands for Universal Robot Description Format. And we are going to try to do a scatter robot. A scatter robot is a robot with 3 degrees of freedom, 2 rotational, and 1/3, which is a prismatic joint on the vertical axis, okay? So the idea is that we do something like this using the ROS tools. So who among you have tried to do this? Anyone? You did? And how did it go, Jose? Were you able to do it? Yes. Can you show it? Yes.
Okay, so this is the Urdf file.
Okay.
I basically searched for it and found the basis and worked from there.
That's the way to go.
Okay, so basically first I define the material, only the color parameter, the 4 colors that are on SCARA example.
Okay.
After that, I create the base link and the other one, the parent and the son.
Okay.
And I work with 2 directions. I create 2 types of joints. The first one is to rotate, and the second one is just a visual. I call it visual joint, just to get the perception of really rotating. Okay. I can show you the.
Show it to me. Yeah, show. I will see in the end because I'm already curious.
Okay. So basically, the visual joint is just a fixed one, just for purpose of visualization. And this is the coordinates.
Can you go down, please, Jose? Go down.
Yes.
This is the one for the purpose of visual, a joint for the, because for me, for the purpose of visualization would be a link. What is confusing me is that you are creating a joint just for visualization. I would create an extra link for visualization.
I create an extra link.
And then a joint.
And then a joint.
Okay, okay, makes sense. But it is the link that is used for the visualization, no? That's where you put the visual. On 33.
On 33. Yes. No. The visual is something else. I call it visual also. Maybe not the best word, but this is my terminology for the joint. Okay.
So continue. I will try to figure out what you are doing.
Okay. So basically, after that, I just create a link. Here I put the origin and the rotation, and the origin based on the parent, which is in this case the base link.
Okay.
This is the rotation axis, and this is the origin offset between one and another. After that, the link 2, the same thing, which is a continuous in this case. Not the best option, because the continuous will go around for 2 pi. Yes. And it intersects a bit, so it's not the best option here, but I didn't find another one.
There is one called Revolute, which is a rotational joint. But okay, looks great, continues.
After that, the same thing, a visual joint for that. Fixed one, created a link. And then the same thing, visual joint for the grip, which is fixed. And then the actual joint, which is prismatic, translation between an axis, between, I define an upper and
Yeah,
lower level.
that's it.
This is effort. I have no idea what that means, but
Me neither.
so I just put what was there and pretty much it.
Makes sense. Can we see
Okay.
it working?
I can show you the SCARA also. Yes. The launch file. Okay.
One question, which is not a question for you, it's more, I just want your colleagues to listen to the answer. How long did you take to do this?
Probably a morning.
A morning, so 4 hours.
A bit more than that.
Okay, makes sense. That's you are on average, or even better than average.
This is the GUI, which was a mess to put in, but okay.
No, you were the one who wrote some issue, no?
Yes.
It was not a mess. You were just calling the wrong node.
Yes, but until I realized that, it was a mess to discover. So this is basically the robot itself. And the visual joints were this one, and this one. Because otherwise, I would have two boxes just rotating.
Yes, yes.
And I want really the joint itself to be visualized. And that's it. I rotate here. I can rotate here also, and the grip.
Looks nice. Okay, the transformations, you still have one transformation somewhere near the green cylinder, don't you? Are you hiding it?
No. You're calling the axis, right?
Yes, the axis, the coordinate frames.
Wait, now it's there.
It's hidden somewhere?
It's hidden, I think. I saw it.
You can take away the robot model and we can see it. Yeah, well,
no, it's not
another
here.
option is that you've hidden it.
Of course, no, it is.
You know what you can do, Jose? You can add the display type TF that I've shown today in today's class.
I used it first, but the axis and everything else was kind of a mess, but I'll try again. It was too noise.
Yeah, I know
too much noise.
But from here we can see exactly what you did.
Okay.
Can you put the scale from the TF? You go to,
yes.
Put the scale up. Okay, so you have the base link there, starting from the left.
Base link there.
Then you have, what do you have?
This is the base link sun, which is the link that I use for the visual joint.
Okay.
Intersect with that, I have the link one.
Coincident, okay.
Coincident, yes. And the link one with base link forms the joint one.
Okay, so can you please look from the top to bottom? Because we will see that the coordinates of the base link is like this, and then when you rotate, the other one rotates like this, no?
Okay. You want me to rotate it?
No, but I would like you to look from the bottom, from top.
Okay.
If you press shift and then, yeah. Okay, now can you see when Jose rotates the joint base link to link one? Yeah, those two reference frames will change. Okay, that's it.
This one. And then also I have the link one to link two base. This one is just the visual one, the visual joint. Here I have the grip base, which is the visual joint again, and the grip link, which is the actual one who's moving.
Okay. Makes sense.
And I think that's it.
And this is from exercise 6 to exercise 9.
Yes, because I did it almost on.
It's the best way to do all of them together.
I prefer to use a launch file and put everything to run in once.
Okay, so anyone has any question for Jose? Now I'm not really sure what to do because I can try to do it in front of you. Because there are some things which I would make different from what you did, but not so many.
Yeah.
Yes. This part about the visual joints, I think it's the same, but with different names. I'm not sure. But I think I can try to do it for your colleagues to see how I would do it from the beginning to the end.
Okay.
Let's see. So the first thing is that if we are doing a description file, by convention, it should be created within a package which is called the name of the robot _ description. So I just want to make sure that I don't have it already. Yeah, Pari Part1 Scar description. So I will create I will create something similar to this, but not the same. Otherwise, I will have problems with conflicts in the package names. So here I'm going to catkin create package. Let's call it SCARA description or PSR SCARA description, okay? This is a package which will only contain a new RDF, so I really don't think I need this. But as I told you, I always put it anyway because it doesn't affect me. You know that joke about the guy who says the raising fuel prices don't affect him because he always puts 10 euros, so it doesn't do anything for him that the price goes up. Okay, so now we have a PSR SCARA description, which is here. Okay, here it is. Now, I need to create the URDF, and the URDF should be inside a folder called URDF. And the file should be called, SCARA.urdf. So SCARA.urdf, okay? Well, now how do we start? Like José said, when we are starting, we have to look at the tutorials. There is no mystery here. If I go to the first tutorial, there is an example here right away of how to create an URDF. So I'm going to pick it up. So this is my first example. My robot will be called SCARA. I must start, how to say, adding up to the example. So we will define what are called links, elos in Portuguese. And for example, you can think of my arm or a robotic arm. So the forearm is one link. This is another link. This is the forearm. This is I'm not sure, the arm, I think, arm and the forearm. So these are two links connected by a joint, which is the elbow joint, which is a Revolute joint, so a rotational joint. So here I'm going to create the base link. And this base link wouldn't even have to have a visual. Could just be like this, okay? So I can just create first the base link and then link 1, which comes from this example here. So I'm just following the drawing, okay? So base link and link 1, 2 links. Now, how do I connect both? With a joint. So I'm going to pick up a joint example. Okay, here is an example of a joint. So a joint is a way to connect two links, and the way these two links are connected can be of 3 main types, either fixed, so they don't move with respect to the other. So, for example, when we put some casts because we broke the arm, they do not move, the forearm and the arm. This is a fixed joint. Or it can be a revolute when there is when you rotate around an axis, so this is a rotation. Or it can be a prismatic when you have something like this, like a telescopic joint. In this case, we are searching for a revolute. Or you said a continuous, no? Continuous is a revolute continuous. It makes more sense because that way our SCARA can move continuously without limits. Now, whenever we create a joint, which is a revolute joint, a rotational joint, we must define around which axis it will rotate. And here is how we define. So a joint also has an origin. We can put the origin. Yeah. Conseguem ouvir ou não? Yeah, I think it's the room. So I'm just searching for origin, and I was searching for something else. Axis it was. Where is it, the axis? Joint. Axis. Find axis. Strange. I'm lost. Because there was, when we do a Revolute, this is fixed also. I think it's in the other tutorial. Let me go to the other tutorial. Also this. So here, yeah, movable. Yeah. So now here, this joint must have an axis, as I was searching for. And so typically I do it like this. First the axis, then the origin, and then the parent and child links. So by convention, my convention, not really ROS convention, well, ROS also uses something like this. A joint will connect two links. Therefore, the joint's name will always be called the first link, the parent link, _2_ the child link. Okay? So this is base link to link 1 joint. And now, if we take a look at the drawing, we can see that the z-axis is of the base link is where we want to rotate the joint. So we will rotate the joint around the z-axis of the base link, and therefore we say that the axis of rotation is 0, 0, 1, okay, which is a vector coincident with the z-axis. Then the origin will displace the joint to some other place. For example, let's say that this height here of the cylinder, of the first cylinder on the bottom is 0.5. So if this height is 0.5, we have 2 times 0.5, the first cylinder and the second. So here we will put 0, 0, 1. And now we are going to put it to select the child and the parent link, link 1. Okay. So this is what you did, Jose, nothing different, just trying to explain them step by step. Otherwise, it's going to be difficult for them to understand. Okay, now that we have done this, the way to use it is what is explained on exercises 7, 8, and 9. Okay, so this is a lot of stuff. Let me try to, I'm not sure if I have this already. Yes. I can try to draw, or not really, I can just go here. So first, how do we make sure that our robot description file is correct without any bugs or syntax errors? We call this command here. Okay, so this command, if you run it, ROS run, okay. So it has here the SCADA.urdf. So I must be in the place where I have the SCADA.urdf. So I'm going to ROS CD my way into PSR SCADA description, CD URDF, and now I can run my ROS run blah, blah, blah. Okay. So the result of this execution is this output. So this is the interpretation of the file's content, which creates a string. So this is just to make sure that we are parsing the file correctly. So the file is well written. For example, if here I do not close link, name base link, it will give me an error, okay? Just to check to see if my URDF is okay. Now, after I have this, what can I do with it? So this is a description of my robot. Right now, I only have a very simple robot which has only 2 links and 1 joint connecting them. But what can I do with this description? I can do the following. You know that whenever, I think I will draw, it's better. Otherwise, I cannot explain without drawing. Just give me a second to go to the class, to the Zoom session. PSR, e aula P2. Okay, so I'm with my tablet already. Okay. Yes. New note. And okay, preliminaries are done. Now, suppose that we have a robot like the SCADA, where we have here the coordinate frame of the base link. So I have this one, X, Y, Z. And now you have the coordinate frame of the base link, which will be something like this. Let me put the red for the X, Y, Z. Now, if we know that there is a rotational link here with an angle theta, if I ask you, let me just put here, this is the base link. And this is link 1. So if I ask you, what is the position of link 1 with respect to base link, or in other words, what is the transformation from the base link to link 1, what would you tell me?
Defined by 3 by 3 matrix.
Yes, that's...
And the first row, we have cos theta.
Okay, you are going to tell me the real equation? Okay, well, yes, but it's, how to say, my point is not that you give me the complete matrix. You could do it, and it would be rather complicated and impressive if you can really do it. But my point is that this is a function of theta, right? Because we depend on the theta. And if you can compute this, actually, for me, it's a 4x4 because I use the homogeneous format. I'm not sure whatever you use, but this is the rotation, and this would be the translation. And of course, the rotation would be dependent on the theta. The point here is that because this is a function of theta, we need the theta in order to be able to produce the transformation, okay? In ROS, the transformations are in the topic TF. The guy who publishes them is the node robot state publisher. So this is a special node from ROS who's in charge of publishing these transformations. But in order to compute these transformations, it needs, as Gabriel was saying, the theta, okay? So it will receive the theta in a special topic called joint state messages, I think, okay? So there is a topic which contains the values of the joints, of the angles of the joints, angles or positions if they are prismatic joints, which robot state publisher, the node, listens to, and then it will use. So what Gabriel was saying here was to derive the direct kinematics. So it will use the direct kinematics as built by the Deneve Tattenberg. You know this very well if you are doing industrial robotics. So it will compute using direct kinematics the values of the transformations which the node will publish on the TF topic. Okay, so this is a simple pipeline, but this is distributed once again because the direct kinematics is computed by the robot state publisher, but the TFs can be, for example, used by RVs or something else. Whereas, for example, the joint state messages could be published by the robot drivers or something like this. Okay. So again, this is completely distributed, many nodes operating simultaneously. But the focus of our discussion today is the robot state publisher. So the robot state publisher will receive the joint state messages and then the TF. Now, as I told you, the typical publisher for joint state messages is a driver. For example, when you plug in the FANUC up there in the laboratory, there is a ROS package which talks to the FANUC controller and publishes the joint states, the angles of the joints of all 6, I think it's a 6-degree of freedom, all 6 joints of the robot at 100 Hertz or something like this. Now we don't have this kind of robot, so what can we do? We can replace the drivers by something called joint state publisher. The joint state publisher is a special node which is used mainly for debug, which does the following. It will look at the description of the robot and it will figure out which are the joints that are non-fixed, so are movable. And for each of the non-fixed joints, it will create a GUI, so a window, with a slider saying, oh, this is a joint, blah, 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 joint X, and then you have a slider here where you can move the value of the joint. Whenever you move, joint state, oh, out of battery. Joint state publisher will send this message to the in the topic joint states, which arrives to the robot state publisher, which then computes the direct kinematics and sends the TF messages. Okay, so it was enough for me to show you the pipeline. Now I'm going to implement it. First, how can we run the robot state publisher? We can run it like this. So now I'm going to go out of this. Yeah, like this. So first, robot state publisher. That's it. Clear. So now I'm going to first create a ROS core. No, but I should. Yes, I am. I'm going to share again. Can you see it now? Now I can? Okay. So now ROS core to start with. Now robot state publisher, but the robot state publisher, as I told you, will require joint state messages, but also the description of the robot, because the direct kinematics depends on the configuration of the robot. So if it does a Danavi-Tattenberg chain, it needs to know what kind of configuration of the joints exist in order to do the computation of the direct kinematics. This is done by defining the Urdf, okay? So what we are going to do is to put the Urdf inside the ROS parameter, and this ROS parameter is the one which is automatically read by the robot state publisher. So the way to put this into parameter is this. So what I am doing here is the following. I'm going to do a ROS param set of the robot to the parameter robot description, and here I must put some kind of a value. This value will be, it could be something like this, blah, 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 a string. So now if I do ROS param get of the robot description, there is something there, okay? Now, what do I want to put there? I want to put there the result of the interpretation of the Urdf file. So how do I compute the Urdf? As you've seen before, PSR SCARA description, blah, blah, blah. I have here my SCARA.urdf, which I can compile, let's say, using, we've done it before. Where is it? Here. We've done this, okay? You remember? This is just to display. So we could do this. But the way to do it here is to do a ROS run chacro, or better still, chacro SCARA Urdf. So the command chacro SCARA Urdf will produce a representation of the file's content, which is suitable to put inside a parameter, a ROS parameter, which then robot state publisher will read and understand, okay? So what I want to do is to put the output of this file inside the ROS parameter. So we do it like this. I will just put this terminal so that you can see. So how do I go and fetch the content? Is this way. So if I do it like this, this means ROS param set. The name of my parameter is robot description. And now put there the result of this. And the result of this, I think it's like this. If I do it like this, cross param set. I think it's like this. Okay, so the aspas, I'm not sure how to say aspas, quotes, double quotes or something. The first ones, these ones, Gabriel, are used just because I'm saying there will be a string there. And then the accents, so the second ones, are used to signal, look, I don't want you to write there literally chakra skara Urdf. I want you to write the output of this command. So now if I do a ROS param get, it will contain the output of the interpretation of the Urdf, okay? I don't think I did it like this. I did it in a, did it in this suggestion here. Yeah, okay, it's the same, okay? So this is what I did. Okay, now we have the parameter well inserted into ROS, and now we can launch our robot state publisher, ROS run, robot state publisher, which starts running and is running right now. We can even see what's happening from the point of view of the nodes operating in the ROS ecosystem right now by doing the following. Introspection, right? Okay, so for now you have robot state publisher listening to joint states which nobody publishes, publishing TFs to a single node, which is the RQT, which is doing this debug, okay? So this one is the one which we are seeing right now. Okay, so now the system is still incomplete. What else do we need? So we need RVs in order to visualize the transformations. So we are going to launch RVs. Base link. And now, finally, we need the beginning of the chain. Well, RVs is already there, RVs. Now we need the beginning of the chain. So who will publish the joint states? As I told you before, when my tablet went out of battery, it should be the driver of some robot. Since we do not have a driver, we will launch this special debug node called Joint State Publisher. Actually, the node is called Joint State Publisher GUI, as Jose very well knows, because he was how many hours looking at this? Too many. GUI. Okay, that's it. So I'm going to run from the package Joint State Publisher GUI a node called Joint State Publisher GUI, and this node will do what I just explained before. So it found a single joint which is non-fixed, which is called base link to link 1, and right now I can, oops, sorry, I can see my transformations which are there. I never use this window. I'm going to put to scale up. Okay, so now I have there base link and link 1. And if we change the value of the joint, you can see that this is already moving. Okay, so that's the first part, is to have all this pipeline working and well understood, because this is going to be the core of many things to come. What Jose showed at the beginning of class was a bit more than this, but it was just an addition to this basic concept of having someone publishing joint states, so angles, which are then interpreted or received by the robot state publisher that computes the direct kinematic and publishes transformations. Because now, if my transformations, if my coordinate systems are being positioned somewhere in space because of the transformations, now I can draw stuff attached to these reference frames, okay? So now the definition of these visuals are just definitions of, well, visual components, which are going to be attached, in this case, to the base link. So let me just create a visual, which is going to be a cylinder of 0.5 radius. I'm not sure if 0.2 makes sense. Let's use it, okay? So now my base link will have a visual, and we can also create a visual for the link 1, which in this case, I will not use a cylinder, I will use a box. There is a box here somewhere. Find box? No. Find box? Here, you see? So the box is like a parallelogram where you can define the the size on all three X, Y, Z directions. Sure, Manel.
In the GUI that we have, what if the joint has more than 1 degree of freedom? Does it show why?
There is no joint which has more than 1 degree of freedom. If you have, so there are two types of joints. Prismatic. Prismatics go and move over 1 degree of freedom. Then you have the revolute, which rotates around one axis. Then theoretically you can have a spherical joint. Those have more than 1 degree of freedom, but I don't think they are supported in ROS. Nor in most of the softwares I know, I think. This is just a theoretical concept. Actually, in robotics, there are some special hands. There was a hand, what was it called? I forgot the name. But there was a robotic hand which tried to do something like this, because I don't know, our muscles, I don't know if you know how they work. It's like a set of strings where you can pull. So for example, you have some strings like here, which you can pull, and when you pull, it goes like this. And then you have some other strings here, which you can pull, and it goes like this. So this is like a spherical joint, or almost spherical all the way, but this is very hard to do in robots. And for example, not only the actuation itself, but also, for example, the encoder. How would you know the position? You cannot put an encoder in these two axes. So this is not often used in robotics. So we usually Revolute and Prismatic is more than enough for us. So moving on, the box size. Now I have to take a look at the size of my box, and let's say that I want to represent this blue part. This is going to be one of the differences with respect to you, Jose. So this blue part, let's say that is going to be like a box. The height of the box will be the same height as the yellow part. So let me put here the height of the box, which is Z, also 0.5. The Y can be the same as the radius. So the radius was 0.2. And the size, the length, let's say this is 1, 2, 3, 4, 5. Let's say 5 pieces. So 2.5, right? No, 5 pieces of 0.2. So this is 1. I think so. No, not 0.2, 0.4. Because 0.2 is the radius, no? 0.4 vezes 5. I think it's 2.0, something like this. Yeah. Okay, so now what must I do? So now, once I do this, it's still the same. Like I cannot do anything, so I don't see anything. I need to add a special kind of marker of display, sorry. I always call them markers, these are displays, which is the robot model. The robot model will do what we've been discussing. It will go through the robot description and figure out for each of the coordinate frames, which it already knows where they are because of the transformations, to see if they have a visual component. If they do, draw the component. Now, we are not seeing any change here in RFEs, even though we added this new display, because we have to update the description, the robot description. So you remember that we had to run here the update of the robot description, which was done like this, okay? So again, update my robot description. Now, again, use my robot state publisher. Robot, yeah, okay. And let's see if RVs already prefers what the, okay. Now we can see this with two components, one cylinder connected to the base link and one parallelogram or box connected to the link one. So now what we are going to do is just try to put those two together. For example, notice here that where the coordinate systems are is not necessarily the center of the bodies, of the visual bodies. For example, the cylinder on the bottom is positioned, so the center of the cylinder is coincident with the origin of the base link reference frame. However, what we want is for the base of the, for the center of the base of the cylinder to be coincident with that same origin. Therefore, we need to somehow shift the visual component up. This is done by adding here an origin inside the visual, okay? So this is like draw something, but displace it with regards to the link that we are identifying here. So in this case, I want to displace it up therefore, and this up will be half the height of the cylinder, which is half of 0.5, which is with 0.25, okay? Now, again, I must shut down my description of the robot and update it, run again robot state publisher, and now I should have something updated, which didn't happen. Strange. Ah, ok, obrigado, José. So, here. Anyway, are you guys tired already of having to shut down this, update that, blah, blah, blah? Yes? Okay, so might as well do a launch file, right? So we can, of course, do a launch file. Again, as I'm following completely the ROS convention, I will create a new package, which is called PSR SCADA bring up. So here, so I'm going to shut down everything here. Well, okay, I will shut it down. So where am I? Here. Now here, I have a catkin make somewhere here. Catkin create package, okay. So this is going to be PSR SCADA bring up. Okay. So new package, a bring up one. In this bring up package, I'm going to put, I always forget the shortcut for the Git add. I think it's Control-Shift-A. Okay, I always forget. Okay, new folder, new directory, launch. Inside I have the bring up.launch, which, by the way, whenever that launch is just a visualization, just RVs, and whatever RVs needs, sometimes it's always called visualize.launch. So I'm going to create a visualize.launch. Now, of course, I need to somehow figure out where an example of a launch file, which I will search, for example, no, not here, bring up. Okay, here's an example of a launch file, which I will copy and adapt later on. Okay, so this is the launch file from this morning. And you can see in this launch file that, so now we need to think, what do we need? We need everything we launched before. First thing, we were setting a new parameter. So we can just try to set a new parameter. Actually, that is the example of a launch file, so I can just copy it here. So might as well copy. I don't have to explain. Then I will explain. So here I'm going to create a variable called model, which by default is the finding of the Urdf, which we know is called SCADA, and is inside the package PSR SCADA description. Okay? So this is my variable model. My variable model will be used there. So what are we doing here? We are putting on the robot description. We are creating a parameter called robot description, which is populated or which is set using the command find chakro something. I think I can just replace this by chakro, because in my terminal I can just run chakro. Okay. So I think I can do this. Then the GUI, that was because you could either use the joint state publisher GUI, or you could use the joint state publisher with a parameter to set the GUI. That's why this GUI was here, but now we don't need it because we use this. So substitute publisher by publisher underscore GUI global. Okay. So now we have the joint state publisher and then the robot state publisher. So we are launching everything all together. And we can also launch RVs, which is here also. Well, actually, I will create a new file called, I will create a new file, better still. Copy, paste. So this is going to be the bring up. That way I do it exactly like I usually do it. So we have a bring up.launch and a visualize.launch. The bring up is responsible for bringing up everything, including the visualization. But in the visualization, we just launch RVs and whatever we need from RVs, which is this. So you are going to say something like this. Okay, is there a configuration file? If you don't give me one, I will use the one which is in PSR PSR SCADA, bring up, config, SCADA.rvs. So now, of course, I need to create this file, this folder. Config. It depends on the launch files. Sometimes you have so many. For example, look at the Rustbot. You can, the way to partition is very debatable. I had a student there, so I stopped discussing the partitions when I had a student that did. So I had a code, I gave him the code, and I said, okay, try to use this code. And the code was like 2 or 3 files. And when he came back after 1 month, he had 100 files. The same code, everything is split. So it depends on whether you want. For example, here the bring up contains all this. So you might as well start separating stuff. Otherwise, it's going to be impossible. And so you see here the visualize. It contains just the RVs, yeah. This is but this is the way I do it. It's not really a raw standard. So here we go. So we need to create this file here, okay? Then afterwards we will create it. So we have 2 launch files, one called visualize.launch and another called bringup.launch. And now we need to call the visualize from the bring up. So the bring up will not only run a couple of things, namely creating a parameter, creating an argument, creating a parameter, launching 2 nodes. It will also call another launch file, okay? So it's like a hierarchy of launch files. So how do you call the launch file? I have to search, I don't know, include something. Not chakra include, not this. Oh, yeah, where is it? Okay, let's Google. Horse launch include. Okay, there is no example. Come on, I need an example. Oh, come on. Okay, so let me search somewhere else. Perhaps here. Yeah, here for sure. All.launch will certainly include some other stuff. Include, Taki. Okay, here. This is an example. Copy. Let's copy and then understand. So I'm including a new file. Where is this file? It's in my package. PSR SCADA bring up, launch, visualize.launch. Okay? And is there an argument needed? There could be an argument, but I'm not putting any argument so that it selects the default value, which is what I need anyway. So no arguments here. And that's it. I already have the inclusion of a second level launch file. So all this gigantic parentheses just to take care of the launch file so that whenever we want to change a little bit of the URDF, we just launch again easily. So now ROS launch, PSR, SCADA, bring up. Now I have 2, bring up. Okay, so there was an error here, which was robot state publisher, state publisher. That's because the node now is called robot state publisher and not state publisher and not state publisher, exactly. So here I must change to robot. Okay, new attempt. Okay, now I have to save the configuration file in the proper place. So let's first let me add here. I know this is going to be base link. And I know that I want to show the TFs. And also I know that I want to show the robot model. Okay. And so now I have this configured. I'm going to save configuration as, and I have to go to the proper place. Because I said here in the launch file to load. So I cannot see it here. Let me put it here. Okay, so here I'm saying load RVs. So load from the package RVs, the type, the node RVs. Minus D is read this configuration file. And this configuration file is the config scar.rvs, which does not exist. So what RVs did was, oh, doesn't exist, I'm just going to load the default. PSR, part 11, PSR SCARA bring up, config. I called it SCARA, no? RVs. Yeah, let's see. Okay, now launch again. Okay, now RV is completely configured, okay? The good thing now is that if I change something on RVs, for example, oh, these TFs are not nice. Oops, sorry, not this. These transformations are really not nice. They should be bigger. And I also don't like this. So whenever I'm already moving the configuration, now there is an asterisk there. The asterisk means the configuration is not saved. So now I'm just going to put, for example, the TFs bigger, okay? And the asterisk, I'm going to take it away because I'm going to push Control S. This is a save, no asterisk. That means that because I loaded already the proper configuration file, I can change it and save it again. And that way, this is very convenient because now I launch it again and I have an updated configuration for RVs, okay? And now we are in conditions of continuing to change our URDF. So first thing, I like the transparency of these boxes. Oh, but I'm not defining the, wait, not there. Let's first go and try to put the red box in the proper place, okay? So it should go down half of its height. So to go down half of its height is something like this, I would say. Minus, this is, the height is 0.5 also. And now it should go forward around the X component, I would say half of its length. So the length is 2, so it should go forward 1. Let's see if it works. Okay, now it makes sense. Okay, so we are already moving our SCARA robot, and everything seems to be okay. Now, a couple of, where is it? Yeah, it's okay. Yeah, this reference frame should be on the top as per the drawing here. Okay, so this reference frame is there on top, so that's okay. Now, what can we do extra? Well, we can change the color of our bodies. So this cylinder and this box could be with different colors. By the way, the box should be larger, no? Wider. Why is it so thin? Did I make some mistake? 0.2, ah, yes, because it's 2 times 0.2 because of the radius. That should be the diameter, no? No, it was because the 0.2 was the radius, and we want it to be the same as the diameter, okay? So now, what José was saying, well, before we go into José's discussion, let's first try to put this with different colors. So for colors, we use the material, which also José showed, material. So we can say here that we have a visual, which is a box of material white. The material we define like this. So let's try to define 2 materials. I usually do this definition on the top. Materials. And so we need some blue, which I think is like this, from what I saw. And then we need some yellow. which again, from what I saw this morning, should be like this. I'm not sure. So a blue and a yellow. And now the first link is supposed to be yellow, which we do by saying something like this. Yellow. And the second one is supposed to be blue. Try again. Okay. Ah, my yellow went wrong. I never know what is the yellow combination. Never. I cannot memorize this. Let's see if it is like this.
1, 1, 0, 1.
Okay. I think I made. Okay, now it's correct. See? Okay, so also something that would be interesting is that we have some transparency in the bodies so that we can see inside. So we can change here the value of the alpha. Here we go, again with an alpha. Okay, looks much better, no? Now, what José was saying was the following. Oh, this is quite nice, but now the problem is that this box that I have here does not show, well, has nothing in this region. So this doesn't look like a rotating body. So the one thing that would be very nice is if we could add here another cylinder of the same size as the yellow cylinder, but shifted upwards so that this rounds out this part here. Now, our first approach would be to say, okay, so we have here the base link, no, sorry, the link 1, and this has a visual, which is the box. We could add a second visual, which would be this second cylinder. However, this is not possible because a link can only have a single visual, okay? So what he did, and I think makes sense, is to create a second link, which is only built to support the second visual. So this is what he did. So typically for these, I would call them to try to make it explicit that this is just for visualization. So you called it, what really confused me in your explanation is that you were always talking about a visual joint, but for me this is a visual link. So this is link 1 visual. And now my question, where should this link 1 visual be? Don't worry about the visual component yet, because this is a common mistake. First you start thinking, where is my cylinder? And this is not the way to go. First you have to think, where is my coordinate system? Because then the cylinder will be placed with respect to the coordinate system, okay? So I will even do it like this. First, I'm going to say there is no visual here. And we are just going to define where link 1 visual is supposed to be. Of course, for that we need a second joint. And what do you suppose that we should do? Let's create a second Revolute joint from base link to base link 1 visual. Would you think this is advisable? We could do it, no? We could create a second Revolute joint well, you are looking at me a bit confused. Let's do it until the end, okay? That's it. Now, if I run it again. Now, joint state publisher, as I told you, what it does is it searches for all the joints which are non-fixed. Now we have 2, and then it has here 2 of them, okay? So this one here is the one that controls the position of the link 1 with respect to base link. And this, the second one here, is the one that controls the position of link 1 visual with respect to base link. Okay? So this was just to show you that it doesn't really make sense to have 2 joints for these 2 links. Link 1 visual should be fixed with respect to link 1. So if link 1 moves, link 1 visual should move as well. So my suggestion is to do something like this. Link 1 to link 1 visual is a fixed joint. And now, because this is fixed, we have no axis. And now, where is it going to be? If we do it like this, with no difference here, what we will have is the 2 systems being coincident. However, for me to draw the cylinder, because I know that the cylinders are drawn in the middle, so the middle of the cylinder is in the origin of the reference frame, what I will do is I will put my coordinate frame where I want the cylinder to be, where I want the center of the cylinder to be. So I'm going to shift the coordinate frame down, which means minus 0.25. That means that when I draw my cylinder, my blue cylinder here, I can draw it without any kind of displacement with regards to the link 1 visual. This is supposed to be the cylinder, so I'm going to copy from here. So same size cylinder, different color. I think that's it, okay? Does it make sense to everyone? So let's try it. Okay, again, a single joint. Now we have a pretty cylinder there and a single joint. And when we rotate, it rotates both the link 1 and link 1 visual. I think this is what you did, no, Jose? Yeah, probably is not a good one. What do you mean, probably?
Probably more or less.
Okay.
Different coordinate systems, but
Ah, yes, okay. Sometimes it's not there, it's a bit up, okay. And you have to adjust, okay. This is my way of doing things, but it's not the only one or even the best, I would say. Now, what we need? We need just to add the next steps. I can do it, I think we have lots of time, so I can do it. So I'm going to add a new link, which is called link 2. Link 2 is going to be, I think it's the same size, more or less, yes. Let's say the pink part is more or less the same size as the blue one. Therefore, I don't touch that part. The origin should also be the same. I just need to put a joint here. So the joint will be between link 1 and link 2. It is going to be a continuous revolute around Z axis, yes, with an origin. I think now it does not displace in Z because you see from here to here, there is no Z difference. There is only difference in the X coordinate, which is, I think, the same size as the box. So I would put here a 2. I'm not sure, but I think so. Link 1, link 2. Everyone agrees? Let's try it. Yeah, okay, yeah, let's put a different color. Material name, we need the pink material. Jose, tell me the pink, what is pink?
I don't have pink, but I one half red, half blue.
Half red, half blue.
Something like that.
Now we see if you know what pink is, Manuel. Pink. And the bottom one is supposed to be pink. Okay, again. I would say this is your pink is very. Let's see here, pink color. Pink color. Actually, I have, yeah. Tell me again, Pedro. Okay. Okay, that's it. So now we have two links again. And if we change the other one, okay, nice. Now we can do, again, a purple cylinder to be there. Like we did for link 1 visual, let's just create link 2 visual. So it's kind of copying and adapting this one. So I'm going to copy this. Actually, it depends. I mean, sometimes I like to put the links together with the joints. Sometimes I put, sorry, I copied this not well. Now, yes. Sometimes I like to put all the links and then all the joints. In this case, I would prefer to do something like this. Materials, base link, link 1, I would say. Okay, so the link 1 will contain the link and the joint, which supports link 1. Then I would say visual link 1, same idea, yes. Then I would say here link 2, and here visual link 2. Okay? So now changing this. So this is going to be linked to visual, and the color is going to be pink. Should be the same size, and the joint is going to be called link 2. By the way, that name should be wrong. Yeah, there is a K missing here. So link 2 to link to visual. And I think that's about it, no? I think I changed everything that was necessary. Let's check it. Okay, now we have the cylinder there. This is just aesthetics, not really functional. Yeah, this is just aesthetics. You see there? It's just for us to be with a nice round corner there, okay? That's the cylinder there. Okay, all we need now is a prismatic link, and I can also do it. So for the prismatic link, we can, again, we know that we are going to need a link and a joint, so I'm just going to put here link 3. Let me take a look at the drawing. So this is link 2. It's called EA. Legal. You can hide it here. Actually, you can show the axis that you want. For example, you can do it like this. Yeah, I just want to show everything so that you know everything that is going on. But yes, you can hide them. Okay, prismatic 1. I know that this is going to be called EE link. EE stands for end effector, which is the end of a robotic manipulator. Now, for the origin, I'm not so sure. This is going to be a cylinder, so let me pick up a cylinder of length, I would say the same length with a smaller radius. Okay, and the color is green. So let's pick up the green material. RGB, this one I know. Okay, so we have this one. Now we go back here. So we have a cylinder with the material green. The visual part, I'm not so sure. So for now, let me just put this on 0, 0, 0. And let me just make sure that I have the link 2 to a link well positioned. So I know this is going to be a prismatic joint. The prismatic also has an axis, so I'm going to be, it's like a telescope over the Z axis, sorry, not the X, Z axis. The origin here, with respect to link 2, will have to be all this length here. So this is the length of the box, which is 2. So I think that is okay. And also the Y and Z, I think is okay. So EE link. Okay, what I'm not sure is okay is this part, but let's see it afterwards. Go ahead, Jay. Okay, yes, you're right. So whenever we have a Revolute joint, which is a prismatic joint, or a Revolute joint, which is not continuous, we need to put here what is called the limits, which are not here. I'm not sure where they are. Perhaps in this tutorial. Find limit here. So we have to define this. Copy. So this joint will have to have some limits defined. Effort, I'm like Jose, I don't really know what this means. -1 meter and 1 meter maximum. Okay, something like this. So this is just to define the upper and lower boundaries of the joint. In this case, because it is a prismatic joint in meters. If it was a Revolute joint, it would be in radians. And I think that's it. Let's try it again. Okay, so we have there our green cylinder. Now, the cylinder is should be displaced vertically down, so we can already do that. The size of the cylinder should also be taller, I would say, for example, double the size. So if this is double the size, where is my cylinder? Is the A-link? Where is my A-link? On the bottom? Ah, I was getting confused because of this comment. I was looking at the comment. Okay. Now, first the length, double. And now I want to go down half the length. Okay. Again, let's try it. Okay, so there is the cylinder. And now, if we move the third joint, it is going to go down, up and down, okay? 1 meter up, 1 meter down. Now, if I wanted to have, notice here that in my joint, the value of the joint is there. So if I go to the right-hand side, the value of the joint increases. And what happens when this increases is that the cylinder goes up. Can I change this? Can I do it that whenever we do an increase, the cylinder goes down? What? How can I do that? Any suggestions?
You can define the upper stretch with a negative value, maybe?
We could try. I don't know if that works. I don't think it does, but let's try it. That's a good creative way of trying it.
You can also do the negative.
Could be. Let's first try this one. My feeling is that it will not move. It does move. It worked. I'm very surprised with this. Surprise. Nice. Okay, so this is one creative way. Manel, you were saying another. You were saying the velocity. And like this, no?
Yes, exactly.
Let's see. Nah, it goes up when you put it positive. I don't know what the negative velocity does actually. Okay, very creative, but doesn't work. My suggestion would be that you have the standard here. So you also go from -1 to 1 with a positive velocity, but you have an inverted axis. So instead of going on this direction, you go in this direction. And this also works because I've tested before. So now when I go to the right, it goes down. When I go to the left, it goes up, okay? All right, so I'm not sure what else we can do here. I think that's it. Any questions?
Yes.
Go ahead.
I've noticed that we can put mesh files in here, but the mesh file is kind of a box. So I was wondering what is the workflow to put a complex object in here. Let's say, for example, that you have a car, something like that, and you want to distribute the axis between, I don't know, the wheels, the steering wheel, or something like that. How do you partition the box itself?
When I show you this example here, no, not here. Wait, let me search. I have to search.
But you don't do the complex model with the...
No, the model is not articulated. But let me show you first and then we discuss. Might as well speak with something in front of us. Here, yeah. Now, Onde é que isto estava? Yeah, here. This model here. This is in RVs. But this model is a complete model with so we have a complete model of the car, the wheels, everything is just a single model. It's like as if you go to, como é que é aqueles sítios dos sites, do Google, dos desenhos? No, something else. I forgot the name. But it should be some, how do you say it? Thingiverse? How do you spell it? Iverse. Like this? Thingiverse, okay. I didn't know this one. Yeah, this kind of stuff I was saying. So you can just go there and start searching for a car. I lost some time. I think it was me who found. I found the first one from the Atlas car. So here, by the way, this guy here. This here is a CAD model of a Forge Court, which I bought online many years ago. I don't tell you how many. And for the second Atlas car, I'm not sure. I think we found it or bought it. I'm not sure. In any case, this is a single CAD model. Okay. No, in this case, no. For example, for the Agrov, yes, because this is articulated. But for the Atlas car, no, I think. We do, it depends on the model. For example, for the Atlas car, we don't. But for example, the Agrov, the wheels are articulated. But what we need when we want to articulate is to have split CAD models. Yeah. For the Atlas car, we only had one CAD model, but you could do it. For example, you can pick up the Atlas car model. I will tell you where from. Sarah, you have to tell Jose the assemble exactly. Not the assemble because it's not even assembled. This is not like a CAD model from SolidWorks. This is a CAD model from the designers. So it's a triangulated mesh, yes, but it's not like you have a portion which is just the wheel, which you can easily disassemble. I will show you. Sari is working on this. So Atlas car description, Urdf. This is a chakra, which then will point us to the Atlas car model, which is this Atlas car description meshes Mitsubishi blah blah blah. So if you go back, meshes. Yeah, this is stupid because the only thing that it has is the radiator. Yeah, it needs a JPEG just for the radiator. This is very strange. Anyway, I will download this. No, not like this. Well, I have it here. I don't know why I'm downloading. File, open recent, calibration, new window. Sometimes, yes. For example, for this robotic system, yes, for sure. For the Atlas car, is there any, do you gain something from seeing the wheels turning? Not really sometimes. But for the robotic arm, yes, you do.
Not just the wheels, maybe the sensor itself running around.
But the sensors don't move.
No?
No, the sensors are fixed. In any case, in this case, the sensors are articulated. Well, we can show you this to you. Look. Look, the sensors are moving. You see the lidars there? They are moving. That's because we have different CADs, one for the car itself. When I say car, I mean the chassis with the wheels and everything, and then a CAD just for the 2D lidars, and then a CAD for the cameras and blah, blah, blah. Yeah, but this is only interesting if you really want to move the sensors with respect to the vehicle, which in this case we do because we are in fact doing the calibration. Let me try to focus. I forgot where I was. I wanted to show you something, but I forgot. I know. Let's try to put the car here in the end effector. Let's just put a gigantic car there moving up and down, okay? Let's call this the car pickup, the car pickup or something like that. So what can I do? I have to go to here. So Katkin workspace. source, calibration, robots, Atlas car, description, meshes, and I will copy my meshes to my SCADA bring up. Okay, copy the meshes. Okay, copy everything, blah, blah, blah. Now, for putting a mesh there, the way to do it is, for example, instead of saying that my end effector link will contain a geometry, which is a cylinder, this is like a geometric primitive, cylinders, cubes, blah, 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 torus. I will put there a mesh, which I don't know how to do, of course, I have to search. It's there, the DIA. There, okay, so I just say mesh. Okay, so out with the cylinder, in comes the mesh. This is going to be the SCADA PSR, SCADA description meshes, and this will be the, how is it called? No, where did I put my mesh? Oh, is it? Yeah, I put it in the wrong place. Thanks, Lucas. Okay. Okay. Now, SCADA description meshes. Now, Mitsubishi we have. I think it expands. No, Mitsubishi underscore Miev.dia. I think that's it. Okay, let's see whether or not it likes the. Yeah, it's taking long. So, okay, so now we have the Mitsubishi, like, let's just move it around as if, also, do you see how your teacher is so strong, it can move a car around? Okay, so this is just, yeah, we can do it, no problem. In this case, this is, how to say, I missed the word, transparent. I wonder why. I think here I should do something like a material. Yeah, the material green is transparent. So I just have to put here a material something else. Let's just say here material non-transparent white. 1111. And how do I go there? Yes. Again, second attempt. Yeah, here we have our Atlas card, you see? This is what we use for showing the Atlas card on those videos, okay? So that's it. What else can we, any other questions? Go ahead, Manuel. Sure, launch file. Which one? Perhaps you forgot to put here the robots part. Was that it? GY, yeah. So let me ask you now, do you have some time to work on this? I see that Jose worked, but apart from him, I think all of you didn't have a lot of time to work on this, right? Be honest, be honest. This is the part where you can say, yeah, be careful because this is really going to start building up and up and up, and it's going to be difficult to keep up. It builds up and up, and so next week, well, next year, we are going to discuss about, Manuel, sorry, is it okay? Next week, I forgot what we are going to do, but I can show you. Yeah, to try to catch up. Let me show you what we are going to do next week. This is 12, no? I forgot what 12 was about. Yeah, so we are going to start with simulation, gazebo, okay? So we are going to start working with the simulation, and we are going to do first a simple simulator and figure out how it's working and what it's doing. And then we are going to jump into gazebo, which is a simulator that can simulate real robots. In this case, we are going to simulate a turtlebot, which is an autonomous vehicle, very small one, from ROS, a turtlebot. And so you can see here that we are already doing very complex launch files, then combined with chakras and all this kind of stuff. So it's going to build up more and more, okay? So you see here a chakra. This is a file, which is what we asked for in the, yes, the last exercise. Where is it? I'm going to search for it. PSR. So, part 11. Okay, so the last exercise, I think, no, not the last is the PR2, but yes, the last one, exactly. So the chakra files is just another way of doing an URDF, but with a more, not simple, it's a bit more complicated still, but it is a way where you can put, for example, variables, this kind of stuff. So if you try to do your description instead of with an URDF, you can do it with a chakra. For example, here you have a set of links, actually a single link, using an URDF. What you can do is create some properties, which are like variables, okay? So for example, if I do my description of the robot with a chakra, typically what I do is something like this. I'm going to, I'm lost, I'm trying to figure, yeah, here, URDF. So I'm going to create something called scara.urdf.chakra. This signals that this is a chakra file. And I'm going to try to change stuff, okay? So how can I change this stuff? By the way, I'm going to start using this one instead of the other. So here, instead of calling the scara.urdf, I'm going to call the scara.urdf.chakra to make sure that I'm using the updated one. So typically what I do is to test if all this skeleton works. So before changing anything, I'm going to run again just to see if it still works. So it still does, okay? Now, did you notice that here we had to do some math on our own? For example, here, we were trying to define the length of the cylinder, the height. And this 0.5 is the same as this 0.5 and that one on the bottom. So if I tell you now, can you please put it bigger to 0.7? You have to change here, then here, then here, because this is half of 0.5, then here also, and oh my God, we are changing on 10 different places. So this is the perfect case for the introduction of a variable, which are called properties in chakra. Oops, sorry, undo, copy, paste, yeah. Now, yes, so we are going to create a new, I'm not sure if this is, I think that yeah, I think that's it. So chakra property, the property is going to be called height. So this is the height of our bodies, and the value is going to be 0.7, okay? So now, when I want to use my height, I just do it like this, okay? So for example here, let's start with 0.5 to make sure it's all the same. So where is my 0.5? Here. So I'm going to replace it with the variable height. And oh yeah, this is not a good substitution. You're right. Thanks. There I am. height. Okay, this is one example. Actually, from here onward, well, this is also half the height, right? So here, Chakro also allows us to do some computations. So I can say, okay, let's just see if it works like this. Not sure it does work like that. Chakro cannot load parameter. Yeah, the chakro is not well formed. I'm not sure how to do a chakro. So I'm not sure. Let's see, chakro property, chakro property. Yeah, no, not macro. No, I think that's okay, the math. I think. No, that's not it. It's the upper part. I think this robot blah blah blah, which is well, I have to search for a chakro example that I have. So let's search for a chakro. Okay, here's one. So robot name or something like this. Should be the same. Let's see. SCADA. Let's try again. Okay, that's it. We needed that strange stuff here. I don't know why. Okay, but now we have we are using a chakro and it's still working properly. No problem. Okay. So chakro is useful for defining variables, for doing some math, and even for including other chakros. So with chakros, you can do something, again, a hierarchy of chakro files, okay? So you can split the files, a single file into many and include, like the launch files. You have one launch file, which calls another, and it's the same for the chakros. You also can do some very complex stuff with chakros, which is what they call here macros. Macros are like functions, okay? So a chakro macro is like a function where you have some values that can be given to the function. So the arguments of the function. I can show you an example. So I'm not going to do anything more with the chakro. You can just test it then. I'm just going to show you a complex example that we did, which was really difficult to do, to put working. For example, here, we were doing the chakro of the robot. This is what with Daniela, the large C cell, the description, Urdf. So the large CC dot, I think this is the gazebo, Urdf, large CC Urdf dot chakra. So this is the Urdf for the, I'm not sure if you know what the large CC is. So the large CC is this that you have there on the robotics laboratory, up there on the top floor. You have this. Okay, so this cell with many cameras and lidars, well, you can take a look. It is like a gantry, which contains many lidars pointing downward and the table with a robotic manipulator in the middle. And the persons go inside and are monitored from every angle possible, okay? The idea is to have a very nice monitorization of what's happening inside this volume in order to be able to move the robot safely around, even if a human is inside. And so, this is the example chakra for that system, okay? So you have several properties, several arguments. Then you start, well, more properties, more arguments, blah, 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 more. Then you start including other stuff. So these are other stuff. For example, here I'm including the table macro, then Danielle includes the gantry, the tripod, blah, a camera, the velodynes, blah, blah, blah. And then you start putting stuff, you declare. These are chakra files, and they, the table. You can see it. So this is the table. The table is more difficult because this is a macro. I'm not sure I want to go to the table. Let's go to the tripod, okay? The tripod is a simple, well, it's also a macro, but it's simpler. It has a link, which is called, name is a variable, which is the tripod. So if I say tripod 1 as an argument, it will create a link called tripod 1, which has a visual, which then contains a mesh, which is a tripod, okay? Then you will also have something else, which is the collision. We will discuss collisions further ahead, so let's not go into detail there. Then this gazebo stuff also we'll not discuss. Then you already know the joints. And finally, the tripod does not only contain a tripod. I will show you. Tripod is for the MMT bot, so I will show here the MMT bot. MMT bot, here. Okay, so this is the MMT bot. The tripod is this part there. On the, yeah, here. So, oh, come on. There. So this is the tripod, these 3 legs. And then the plate is this horizontal bar. And this is what we are building. We are putting an horizontal bar there, which we call tripod plate. Okay. So again, a visual, which in this case is just a box because it's the bar. Also the collision doesn't matter now. And then again, the gazebo doesn't matter. And then we have a joint which connects the tripod to the tripod plate. Okay. And then we have a left support and a right support. So we also build links, which are just links, not visuals, for the left-hand side support, where we are going to put, for example, a Velodyne sensor, and then the right link where we put the camera. Okay. And that's it. So this large CC is a bit complicated, but more than being complicated, what is important here is that this is big, but you already know what you are seeing, okay? It's not so complex, okay? So for example, here's one LiDAR, here is the other, and here is the third. Here is one camera, and then if you need, you put more. This is just a big example. You just did a small example, but it's just compounding more and more stuff, not so much as different stuff. It's because this cell contains 3 LiDARs. Do you know what a LiDAR is? You don't know. So a LiDAR is a special sensor. LiDAR means light detection and ranging. LiDAR sensor, wiki. It's just a range measurement. For example, when you are doing, well, not a good example. For example, we have 2D SICK. Perhaps you know these ones from automation. Yeah. Do you know these ones? Okay, so this is just measuring distances, and they measure it through light. So these are called LiDAR sensors. So these are 2D LiDAR sensors. So what we said about a single plane, if you want to, then you have some, typically these are called Velodynes, which are 3D LiDARs. So here in this example here, I'm going to run it again. We have 3, I think in this example we only have 2. We have 3D LiDARs combined. So we have, so you see that you are seeing the person there, and then it looks like a ghost, another measurement. That's because you have 2 LiDARs producing points which are not well registered one with the other. Therefore, you have like 2 different measurements of the same object, in this case, a person. I can show you the other example. Where is it? I'm lost. Here. The other example, for, yeah, here. Here, I wanted to show you this. So here you can see that you have 2 LiDARs. They are on the ceiling of the structure, so you cannot see them. Okay, but, well, these are the measurements that you have. These LiDARs were used very much for autonomous driving in the beginning. Did I ever show you the video, I can show you a video of a LiDAR, of a single LiDAR. YouTube, my videos, where is it? This, I'm not sure if I showed, I lose track of what I show already. So if you've seen this, sorry. Where is it? Here, no. Here, so this is here. So this is a Velodyne. So you are in a car and you are moving, and there is a sensor there which every second produces 1.3 million points because it rotates and measures around the whole sphere, the whole 360 degrees. So what you are seeing here is instantaneously, so at every second it is going to change, the measurements for all the distances on all directions. So this is a LiDAR, a 3D LiDAR. These ones costed a lot, 80,000 euros at the time. So these were really expensive LiDARs. Now they are much cheaper. Now they cost 6,000 euros or so. That's it, okay. What else? I'm lost. Yeah, what you can do more in this class is, I would say if you didn't do it, try to do this, all these exercises. And in the end, you can take a look at the PR2 by viewing the coordinate frames, okay? And we already did the chakra files. For the PR2, I can show you quickly. So if I go to my back files, PSR, you already have this file, which is the PR2 MIT ROS bag play PR2 MIT demo ROS core. Sorry, loop, otherwise, yeah. Now, if I run RVs here, RVs is going to, in RVs, we can see the axis. I've shown you this in last week's class, but I'm going to show it again because now you will understand it better. Where is it? It was because I wanted to show something else. Now I want to show a different thing, and now it's better to see this. Because I want to see these frames still. So that way my reference frame is base link, okay? Is moving around. Sorry? Yes, so now if I would show you the room would be moving around, okay? It's a matter of relativity. Where are we fixed right now? Right now we are fixed on the robot's base link. Therefore, everything else is stopped except from the wheels that are turning around, moving around, the LiDAR, which is there moving, and the ODOM combined, which is moving around. So these are all the transformations from the PR2. So this is a lot of stuff. PR2 is a really complex robot. You can see, I don't know how many they are, but they are a lot. Now, notice that in this case, we have, well, this is from a back file, and the back file actually ruined the structure, the topology of the transformation tree. So if I show you here the transformation tree, plugins, visualization TF3, what you will see is a lot of transformations. Where is my TF3? Let's run it again. You will see a lot of transformations, but they are all with respect to the, I cannot see my TF3. I wonder why. Huh? Strange. There is another way to do it. So ROS run, sorry, again. I can do it like this. ROS run, TF2, TF, view frames. Okay, so what this node does, it will listen to the transformations for 5 seconds, and then it will produce a PDF, which it could not produce because it crashed. I wonder why. Why did it crash? Come on. I don't know. Let me try it again. So ROS core, ROS back play, and now we can do here ROS run TF view frames. Let's see if it works. I don't know why it's not working. Well, anyway. Anyways, you've seen the TFs. That was the most important part. And just to show you that, for example, this PR2 contains a lot of transformations, okay? Here they are. And if we were able to see, which we weren't, the transformation 3, you would see that this is a hierarchical pyramid of a single level, because all frames go to the base link. You can see these yellow arrows just mean that, for example, this frame goes to the base link and all the others go to the base link.
That's an advantage or a disadvantage?
I would say it's a disadvantage. We are working on calibration of robots. Manel is working on this. And when we found the bag file of the PR2, we were really happy because we said, okay, let's calibrate the PR2. The problem is that the bag file contains this disadvantageous topology. Why is it a disadvantage? Because this is not the topology that you typically have when you run the PR2. So because they calibrated, in the end, they have a different topology, a different tree, or a tree with a different topology. And this, for me, is a disadvantage. It would be much better if you would calibrate, and because you calibrated, you wouldn't lose the topology, the original topology. This is one of the things A10 does. It doesn't change the topology. Okay, so see you next year, right? Don't worry. No, go ahead, Pedro. The image, which RQT? Go ahead, tell me again. Did you try to ROS to sudo apt get install ROS melodic? No, noetic, sorry. Noetic RQT something? Really? Okay, so run ROS run image view. So I can show you here because we, okay. ROS bag play PR2 demo -L. Okay, so now we have this running, and I think now we have a camera, no? ROS bag, ROS topic list. Yeah, we have here an image, which is this one, for example, okay? Which we can see, so first, if you cannot use RQT, you can use RVs, no problem. Then, if you cannot use any of these, you can use something else which is called image view. So this image view will allow you to remap an image to the topic that you want. And sometimes this works. Sorry? Sorry. Okay, sorry. I copied the wrong one. That's the camera. Yeah, right. This one. Thanks, Manel. Okay, let's do it by hand. Wide stereo /left / image raw throttle. No, throttle. I think that's it. Okay, so you can use this also to see the image if you want, okay? Why? So don't ask me about why RQT doesn't work, because you see my RQT. It's like I can't even see my buttons, you see? So why? I don't know why. I think it has something to do with Qt, but I'm not sure. I never wasted. Could be. Well, you have an alternative, so don't worry. Gabriel, you wanted to ask something? No, no question is stupid.
When you create a package, you have on the right page, on the right part of the pie chart, like the dark, the house, the image. But when I create a package, I don't have that. Why? And which is the difference?
The image. So, okay. Okay. Yes, if you want, okay, so for example, here, My packages are like with this icon. That's what you mean? Okay, that's because I installed some plugin, which is not really nice, but you can go to plugins and type here ROS. Yeah, it's called Hatchery, no? But it appears, I think. So marketplace. ROS support, for example, and then you have several. The one that Manel is talking about, it's called Hatchery, which I already have installed. But the problem with these plugins is that sometimes they make PyCharm crash. So you can try to install it. No, it's, yeah, but you can install it. If then your PyCharm starts crashing here, with an, you just turn it off, okay? Sure.
I had a problem here before. There was RPass or ROSPy in Horizon, and I saw this problem going on here.
Yeah, exactly.
No interpreter. But
You,
why? Before I had like Python 3.8 interpreter. Why now that I don't have an interpreter, I understand the problem?
what did you select? I couldn't see. Well, if you don't have an interpreter, it doesn't try to analyze the code. That's why you don't have a problem, because no analysis, no error.
Okay.
So you have to select the...
Because before I have, I think this, and with this, I have ROSPy with English.
Yes, okay. So now now you are, so first it says invalid Python interpreter. So just select the proper interpreter. I'm not sure what you selected because...
The problem just going here. I'm pressing OK, but...
No, but this is not fixing it. This is just saying no interpreter. So go to settings, file settings, better like this. File settings. Yeah. Now in the settings, oops, I don't see the window. I think you only shared PyCharm and we cannot see additional windows. When you share with Zoom, you have to share the whole screen, not just PyCharm. No problem. Stop sharing and share again. I will share so that you can share again, okay? Go ahead. All right, so file settings, as I was saying. Now you go to project interpreter, and now there it says there Python interpreter. Select what are the options. Okay, go to the wheel, the gears on the, yeah, add. Now here you have to put the system interpreter. As I said, I don't like virtual environments for several reasons, but let's not go into those. System interpreter, the third option there. Yeah, it's on the left, Okay, now 3.8, okay, go ahead, okay. And apply, okay, blah, blah, blah. It's already updating. Okay, now, with the system interpreter, and this is why I like the system interpreter, supposedly it is going to be, to do the analysis, the same analysis that the terminal will do when you execute it on the terminal. This is why I like this, analogy. And now it's, I'm not sure, what does it say on the bottom? Does it say it's updating? I cannot see because of Zoom. So if it is updating, after it updates, how long does it take? If you press the blue bar, it shows a window, it pops up a window. Yeah, press the blue bar. Okay, so let's wait a little bit. Anyone else has some question? No? So after it updates, if all goes well, it will start analyzing the code and see if ROSPy exists and blah, 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 all this kind of stuff. Okay? No problem, but we can wait, no problem. For the other, there is someone else here. Manel was saying something. What was this, Manel? Automec? Well, you could have told me. I also want to see. This is a model where the wheels stop. This is from the car from Automec. Nice. Do you have an image or no?
Probably on the wiki.
I can search. Am I sharing the screen? No. Gabriel is. I will go there. Wait. Where is your wiki? Here? Oh, no.
No, it's on the bar on the top. It says issues for grants.
Wiki?
And
Gazebo car?
gazebo. Yes. It may have a name there.
Okay. It's too dark. Let me see. Plus, 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 plus. Okay, very big wheels, but
But the wheels rotate. They rotate. Yeah.
nice.
And they rotate when they walk, and you can change the direction.
Oh, nice, nice. That's nice. Okay, so this is, oh, well, Manel, you should explain what you are showing here. This is from Automech, so if you really like robotics, you should talk to Manel, because he has this DEM Automech. There is a group here in the mechanical engineering department, but not only, there are people from electronics, no? Where they work on, I think, 2 projects, a project with drones, with flying drones, and another with an autonomous driving vehicle, a car, okay? And the interesting part is that they do this to go to a competition. Where is the link? No link here. Facebook, GitHub, yeah, here you go. All right, so if you want to take a look, there is a lot of stuff here, okay? And you speak to Manel. Okay, so Gabriel, is it working now? No. Share it, share it. All right, now it doesn't work. That's because PyCharm is not recognizing the rods in your system. How did you launch PyCharm? Can you shut it down and launch again? Did you launch like this?
No. I just.
Okay. Now you will see the advantage of launching like this. But you didn't fall for the trap. Is it still? It's updating again, indexing again? No.
No.
Only after the indexing finishes, you can say that it is okay or not. Now, yes. Okay.
Okay. Thank you.
No problem. Okay. See you next year, everybody. If you need some help, send me an email, or better still, GitHub issues. Even if you want to wish Merry Christmas, GitHub issues.